But we think, the number of people dying from heat every year is at least about 12,000. And so we know that, heat is responsible for more weather-related deaths and injuries than all other forms of extreme weather combined. And so those are the four drivers: loss of natural vegetation, increase in impervious materials, what we call urban morphology, the three-dimensional aspects of the city, and waste heat emissions.
Dr. Stone is a professor at Georgia Tech's School of City and Regional Planning and the director of Georgia Tech's Urban Climate Lab, where he works with cities across the country to map, measure, and mitigate extreme urban heat.
Well, Brian, thank you so much for agreeing to do this.
He's been recognized with numerous awards. He's authored 2 books, including most recently Radical Adaptation. His work on urbanization and climate change has been featured on CNN, NPR, New York Times, and the Washington Post.
You're the guy, I read a bunch about it, and you and your work and your team at Georgia Tech are just doing fascinating things that I've been really interested in, and I know my students and students up in Georgia and Atlanta are also interested in.
Great.
So I want to start with kind of your influences. I'm curious about you and kind of how you got here and maybe what some of your inspirations are and, some background and maybe motivation.
Sure. Yeah. So I'm in somewhat of an unusual position as a university professor in that I'm in Atlanta, I'm at Georgia Tech. I grew up in Atlanta, from Atlanta, and I got my doctorate at Georgia Tech. So I got my doctorate at Georgia Tech. I left and I was able to come back, which felt like a privileged position. Not everybody can do that. So that was fortunate. But on that journey, I in graduate school in a master's program that was focused on environmental planning, environmental management. I was focused on air quality issues, air pollution, particularly in cities. And as part of a class I took focused on air quality in cities, we learned about this kind of unusual phenomenon known as the urban heat island effect. And that's what got me interested in the issue. I mean, I ultimately went to graduate school because air pollution in my hometown of Atlanta was so severe. This was in the 1990s, and we really had tremendous air pollution problems. And it was starting to have impacts on things like the amount of transportation funding the region could get from the federal government to build roads and bridges. And so the heat island was fascinating to learn about that, how that really can intensify air pollution problems. And then ultimately for me, it became a new way of understanding climate change within cities. And so that's what I've been focused on most of my career. But it started from an interest in air pollution.
Great. Awesome. How would you define urban heat islands or maybe heat islands in general?
Yeah, and so it's a phenomenon that has been observed for a long time. The ancient Romans were aware of this in Rome. Rome got to be a very large city of about 1 million people during the Roman Empire. And with, as today, with that population density, you end up having a lot of buildings, narrow streets, removal of natural vegetation like trees, and even like natural wetlands tend to be lost in urban areas. And so that can really warm things up. And so this was noted by the ancient Romans, first measured in England in the 19th century with reliable thermometers. And that's when we got a sense that, the heat island can be 5-10 degrees. We know today it can be as high as 20 degrees Fahrenheit on a hot afternoon. And so it's a product of 4 basic changes in cities. The first is, as I already mentioned, the loss of natural vegetation. And in my part of the world in Atlanta or in Georgia, that's tree canopy, forest canopy. And so whenever we lose that tree canopy, we lose critical functions. We lose what we call evapotranspiration. So evaporation, just evaporation of water from the surfaces of the tree, the leaves. And then transpiration, of course, is the cycling of water through the leaves as part of the plant's respiration. And then shading. And everybody's familiar with shading and how that really cools off the surface by impeding shortwave radiation from the sun. And so even when that happens in a rural area, it warms things up. So the heat island effect is not only an urban phenomenon, it's also a rural phenomenon. But usually
Okay.
we intensify it in cities because we don't just cut down the trees. We then bring in a lot of impervious materials, roads and parking lots and buildings. And those materials have what we call a high heat capacity, something you might focus on in a high school class, on a science class. But just the ability to absorb and store and re-emit a lot of energy that you get from the sun and the environment. So that added capacity to store, absorb, and store heat really warms up cities once we remove the natural land covers. And then two other processes. One is what we call in planning or urban design the urban morphology of cities or neighborhoods. And that's the
Okay.
three-dimensional characteristics. And so we have tall buildings, we create a canyon between those buildings. And so as sunlight is absorbed by the vertical surfaces of buildings, that heats up the building and it re-emits that as long-wave radiation, that can then be absorbed by the adjacent building. And so we have this trapping effect of radiation that happens in urban canyons. It can be roadways below grade, below the surface, or just tall buildings. That's the third mechanism. And then the fourth is the emission of waste heat, largely from the burning of fossil fuels. And so cars emit a lot of air pollution. They also emit a tremendous amount of heat. And so, you wouldn't want to put your hand near the tailpipe, but you would feel a lot of heat coming out of that, right behind the car, smokestacks, industry, and then mechanical air conditioning systems in the school, in our homes, in all buildings, where we have air conditioning, is mechanically removing heat and venting it outside. And that heat, along with the combustion heat, can contribute to higher temperatures. And so those are the four drivers: loss of natural vegetation, increase in impervious materials, what we call urban morphology, the three-dimensional aspects of the city, and waste heat emissions.
Okay. I think I was listening to one of your interviews on NPR,
Mm-hmm.
and a stat in there I think that you had shared was some cities could be 20 to 25% of the effect is due to vehicle traffic. Is that
Yeah, that's about right. And
the case?
it varies across cities, right? And so, there are really intense districts in large, dense cities like Manhattan, where the majority of the warming can be from waste heat. But typically across a city, waste heat is maybe the third most important of these drivers. Loss of vegetation tends to be the most important. Impervious materials follows after that, and then waste heat, and then urban, the canyon effects of cities. But that can
Okay.
that can switch in a really high density city. But yeah, 25 to thirty
Okay.
percent can be from waste heat.
All right. Well, maybe that ties into my next question. Um, I guess I'm wondering too, in terms of the design, which is a major thing that you study,
Mm-hmm.
is there a measurement for city density, like that would give you an indication, or how would you measure that from aerial footage, or is there a
Yeah, there are
unit
different
for that
ways.
where you could do
Yeah, I mean, the most basic way is population density. And so we just get that from
it?
the
Okay.
US Census. And we can
All right.
see, yeah, census tract by census tract where we have high population district densities. Census tracts are actually designed to capture about the same number of residents. It's roughly 5,000 residents.
Okay.
And so if you've got a census tract that's a small land area, with 5,000 residents versus one that's a large land area, that tells you've got a difference in the density. And so we can look at the
Okay.
area of the census tract and the population and figure out when the
Okay.
population density is high.
Okay. Would skyscraper ability be a measurement too, like
Yeah,
in DC
we can
where
measure
the
built
buildings
density.
aren't as high?
Yep. And so we now have a pretty reliable technology known as LiDAR. And this is something
All
that's
right.
used from airplanes and sometimes satellites, usually airplanes, that can digitally measure those buildings. And it can see how tall the buildings are, it can see how tall the trees are, it can see how wide the streets are. And then you can come up with spatial metrics of density based on
Oh, no way.
LiDAR data.
Okay.
Yeah.
Yeah, I've seen that for, ecology and kind of, wildlife purposes. And I think even for discovering new
It's
civilizations and
amazing. Yeah,
kind
it
of thing.
penetrates the canopy, so you can see through the canopy, or you could see, ruins that wouldn't be visible to the visible eye. LiDAR is a really,
Wow.
it's a cool technology. Yeah.
Okay. So I'm wondering, for your lab, the Urban Climate Lab at Georgia Tech,
Mhm.
what do you work on? What are your current focuses and what are your goals?
So we mostly are partnering with cities to develop what we call urban heat risk assessments. And so most cities don't really know how the heat island varies within the city. And if you think about it, a city like Tallahassee, a city like Atlanta, we only have a small number of weather stations, and they tend to be at airports. And so when we look at the weather, the temperature on our phone, on our app, on our weather app, it's usually telling us the temperature at the airport, at the closest
All right.
large airport, right? And so if temperatures can vary by 10 to 20 degrees across the city, we really need to know where those hot neighborhoods are, because that's where you're going to have your most likely health impacts are in those hot neighborhoods. And so we've come up with models and tools to estimate where heat is most intense within cities. And you would think most cities would know that, but most cities don't know that. They don't really know where the
Right.
hottest areas are. And so we map that, and then we also, because we use models, we use computer models, urban climate models is what we call them. We can run scenarios within the model and say, well, what if we added trees to this neighborhood? Or what if we
Okay.
had reflective rooftops in this neighborhood? How much would that cool things down? And so that is the most central work we do is to partner with cities to map where how the heat is spatially distributed around the city, what populations we think are most at risk, and then how beneficial different strategies, we can just think of it as climate adaptation strategies, would be neighborhood by neighborhood. And we actually can tell the city, we think you need 4,300 trees in this neighborhood, and you need
Wow.
2,000 trees in this neighborhood, because we really need, we're urban planners. And so we need very actionable information that says you need to do this here. And so that's the kind of information we're trying to help cities develop.
Okay. Now, do those recommendations and calculations factor in type of tree also in terms of kind of location of the city
Yeah,
or,
all those things are
you
important.
know, okay.
Yeah.
Wow.
We usually the cities are pretty sophisticated in the sense that they tend to have an urban forester. They know what trees are appropriate for their climate. And
Yeah.
what trees tend to have better success rates of living longer with heat
Right.
stress and drought. But often that's the feedback we get is we're interested in these trees. Tell us how much cooling we'll get if we plant these trees in these areas. And so there's a lot of back and forth to make sure the data
Oh,
is
perfect.
most useful. Yeah.
Yeah. Yeah. I mean, this topic is just wildly fascinating. It seems so integrated.
Yeah.
Obviously we're looking at it from, biology and from an environmental science
Yeah.
perspective, but what other subjects and fields are integrated into your work and the work of studying urban heat islands and climate change?
History. And economics and policy. So, that when we look at the neighborhoods that tend to have the highest heat load, we often find that these were neighborhoods that historically were redlined, right? And so these are neighborhoods where, there was a discriminatory bias in giving loans for buying homes and things of that nature. And so we tend to find that history, different patterns of development over time that were driven by policy or economics, have a big role in why the city looks the way it does today. And so,
Right.
I think whether you're talking about heat or whether you're talking about flood risk, whether you're talking about the health of the local ecosystem, of course, it's rooted in ecology and biology and physics, but it's also rooted in history and politics and economics and culture, right? So it's really when we're talking about our environment, all of these areas come into play in, I think, pretty interesting ways.
Yeah. I mean, do you feel like a detective sometimes, the way you're piecing all these things
It's
together?
the best part of my career, and I'd say this for your students. I mean, if you go into a career that has a kind of a research component to it, it's an active discovery, all the time. And yeah, I mean, maybe we're data detectives in that sense, but it's really exciting to hypothesize something, design an experiment, and then see what you discover. It's a wonderful way to dedicate your kind of productive work.
Nice. Yeah. So what you'd mentioned some of them before in terms of the cities,
Mm-hmm.
but for heat islands and urban heat islands, what are the causes and kind of the effects and impacts? The major cause and effect of urban heat island.
Yeah, so it's the four drivers I mentioned. It doesn't really vary city to city. The importance of whether it's trees or waste heat can vary some way. But that really is a roadmap into what we can do to cool cities back down. And so we need to, work against those things. And so in most of the time, the most effective strategy is if you can naturally support tree canopy because you're getting both evapotranspiration and shading. I call tree canopy a hydrologically active surface. It's a hydrologically active material. We could just have a shade structure like a canopy over a playground, and that provides shade and it cools things off, but it doesn't cool things off as much as also having evaporation off of the surface and transpiration, which we get from green plants. So green plants are the most effective strategy we have. And we know, based on our work, we're interested to know, well, how much can the addition of trees cool things down? And also, is it cost effective? Is this a strategy that will actually
Right.
provide health benefits to us? And so part of the work we do when we partner with cities is we estimate how many people are getting sick from heat exposure and potentially dying during a typical summer. And
Right.
by knowing that or estimating that, we're accounting for both the heat risk, which can be really high, but we also know we have a lot of heat at the airport, right? There are not many trees, there's a lot of impervious cover, but nobody lives there. And so people work outside there for sure, but nobody lives there. And
Yeah.
so where we tend to find neighborhoods that are both hot, they may not be the hottest neighborhoods, but they're hot, and you have vulnerable populations, people who are elderly or have pre-existing conditions that make them more vulnerable to heat. That's where we think you should focus most intently in trying to cool things down. So we account for both of those things. But in general, we can plant trees. We find that in Atlanta, for example, we can reduce the number of people getting sick and going to the hospital from heat by as much as 40 to 50% in some neighborhoods. So
Wow.
it's not just like a marginal improvement; it's a significant improvement directly in health. We can do that with reflective materials, what we call cool roofs, which are just tend to be lighter hued. So like a white roof is reflecting away
Right.
that incoming solar radiation, and that cools off the building. That's also really effective. We can bring in more water. It's not as common a strategy, but having, you wouldn't want standing water, but if you had circulating water, so you're reducing some of the potential for mosquitoes and things of that nature. That cools off the air. It evaporates. When we evaporate water, we cool things down. And then just shading again by shade structures, so not necessarily trees, is effective. And then lastly, reducing waste heat. And so that's the strategy, reducing waste heat, that's most directly compatible with what we need to do for the global greenhouse effect, which is reduce fossil fuel consumption. And so whenever
Right.
if we have an electric vehicle, for example, versus a standard internal combustion engine, that is emitting much less heat energy, and it's using less fossil energy. So it's got fewer carbon emissions and things that drive the greenhouse effect.
Right. Yeah. Actually, I hadn't thought about that. Obviously, you hear about fossil fuels and the energy that goes in, but not the energy that comes out.
Yeah,
It's also a key environmental aspect.
yeah. I mean, if you think
Yeah.
a typical gas-driven vehicle, only 15% of the energy in the gasoline moves the car.
Really?
85%, about 85% of energy is lost as waste heat, and it just warms up the air. So most of the gas we burn is just heating things up. It's not even moving the
Sure.
cars around. So it's pretty inefficient technology.
If I hear you right, it sounds like you're running kind of return on investment in terms of kind of the implementation or the impact of different strategies, but also where you implement them.
Yeah,
Is that
that's
right?
right.
So
Yeah. we
you try maybe the most, the area with the greatest, you know, heat islands or the greatest difference in temperature, and that would then have the greatest impact, short and long term. Is that
Yeah, I mean,
correct?
we're measuring, our version of return on investment is reduced health impacts, right? So we want to minimize health impacts.
Okay.
And so if, that's going to be in
Okay.
areas where we have a lot of excess heat, where the heat island is high, but also in communities where many households don't have air conditioning or don't use it, right? And so even if it's not your hottest neighborhood, but you have a lot of homes that don't have air conditioning, that's where people are more likely to get sick. And so that we want to be able to map that city by city, neighborhood by neighborhood, and say, we know city budget is tight, and that you have a limited budget to reduce these heat impacts. We think you should start in these neighborhoods because this is where people are more likely to get sick and go to the hospital.
Beautiful. Yeah, I hadn't realized that was, the reducing, health impacts would be, it makes sense,
Yeah.
but that would be the end goal.
Yeah. That's the end goal.
I like that.
Yep.
You come up with a bunch already, different impact or management strategies. I read about one, kind of off the wall, urban shepherds, goats, eating kudzu to help, native plants thrive, help with shade and evapotranspiration. Are there other, maybe more interesting solutions that are happening in different places that you might want to highlight?
Sure. I
Or
mean, there are lots of interesting ways to potentially cool the air. Some of them are ancient. I mean, one of the reasons I like this field is that it doesn't just require high tech strategies. I mean, we do
yeah,
have increasingly high tech building treatments for for reflectivity that are really highly effective. That are
okay,
engineered with like nanomaterials to really reflect away all the energy. But there are also some ancient practices that, you know, things as simple as having vegetation on a rooftop. There has, at times, we've used something called an earth tube. And an earth tube is literally a tunnel that goes down underground, and it basically makes kind of a horseshoe shape into the ground and comes back up. And so
okay,
we're channeling, that's oriented towards the prevailing wind. The wind comes into the earth tube, goes down underground, and it cools off while it travels 6-10 feet under the ground, because it's just temperatures are much cooler down there. And then it comes back
okay,
out and the air is cooler. It's not, it's not dramatically cooler, but it makes a difference. And so, we have, this is there's something called wind catchers that are an ancient building practice we tend to see it in North Africa and in the Middle East, where we have very hot and humid environments. And these
yeah,
are, towers that are maybe the equivalent of like 6 to 8 stories tall, maybe 4 stories tall. And they have openings that catch wind and they bring it into the buildings. And so it's just ventilating the buildings and bringing in
okay,
cooler air at a higher wind speed than you would have at the ground level. And so all these things can be harnessed to cool off both the ambient environment outside and inside people's buildings when you don't have air conditioning. And so there are both high tech and low tech strategies available to address
gotcha.
high temperatures.
Looking on the Urban Climate Lab website, saw a bunch of the climate vulnerability maps.
Mm-hmm.
And I mean, first off, I'm fascinated just in the web design and the storytelling that you all do to take the data and visualize it in a way that just makes sense.
Mm-hmm.
You can kind of see it automatically and know what it's saying and what the impacts are. But when I clicked on there, you could go into the neighborhoods and then even pull up a number of different metrics. So I'm wondering if you could tell us what went into kind of measuring and creating those climate vulnerability maps.
Yeah, and so one of the skills you would develop as your students get older and decide what they want to focus on and study and pursue it with their careers is, in urban planning, one of the key skill sets we have is digital map making. And now we call this geographic information systems, GIS.
Yeah.
And so we can really develop very detailed digital maps that users can query and pull up information. All your students have used these maps, of course. And so we can really target these kinds of digital maps to deliver information that you typically don't have within cities. And so what we've done in Atlanta, for example, that's the map we have on our website, is you can
Yeah.
click on your neighborhood. I mentioned before that if you look at your weather app, it's telling you what the temperature is at the airport, which is a long way from where you live. And so
Sure.
how hot is it in the neighborhood where you live? What is the tree canopy cover? How much of the urban forest remains in your neighborhood? How much tree canopy is there? And how likely are people to get sick from heat exposure? We can kind of package all that information into a digital map. And then we're
Yeah.
really empowering people. We need cities to take action to plant more trees and have cooling centers and make sure they're making people aware of hot conditions. But it's also, it's entirely feasible and needed for individual families and residents to make improvements in their own homes, in their own properties, where they can, or their own neighborhoods, to increase the amount of green cover and try to minimize the amount of impervious surfaces and heat that's being emitted that's making the city hotter. So we're trying to both help the city figure out what's most effective, but empower residents of the city to also take action on their own and to know what their heat risk is. Because most people don't really know what their relative heat risk is within the city.
Yeah, I really look forward to this, your whole project expanding even further and, municipalities and cities, checking in on that as they're building, for construction and building design and or even families moving to a new city
Right.
or,
Yeah.
as you're saying, family, doing remediations or improvements on their own home.
Yeah.
Having these kind of resources would be, just incredibly helpful.
Yeah. I hope so. Yeah.
Yeah. I'm wondering, and a lot of this you kind of covered already,
Uh
but
huh.
why do you think it's important for high school students, in elementary and middle school to be learning about heat islands and urban heat islands and climate change?
Well, it is, climate change in general is going to be one of the great, challenges of their lives. It's already having, significant impacts on our lives. And that takes the form of, extreme weather like hurricanes. That's what we see
Yeah,
most dramatically. But really, it's easy to assume that that's the biggest kind of health threat to us. But even, dramatic hurricanes, tornadoes, we don't see as many people being injured and dying from those events as from heat every year. And so, in a typical
really.
year in the United States, maybe a couple hundred people will die very regrettably from things like hurricanes and tornadoes. You can have really extreme events where those numbers are higher, but it's rare that it's more than maybe 1,000 people in a country of 300 million. So, that's still a pretty low number. But we think, the number of people dying from heat every year is at least about 12,000. And so we know that,
Wow.
heat is responsible for more weather related deaths and injuries than all other forms of extreme weather combined. So it is the most deadly form of extreme weather. It's also mostly invisible to us. And so we don't have as much awareness of heat. And so I think it's really important for students today just to recognize that heat is a significant health challenge. It's a significant environmental stress too, for the natural environment, and to be aware of what the signs are of heat stress amongst themselves and in their family members and friends,
Mhm.
and then to be thinking about what they can do in their own life to reduce their exposure to heat, but also how they can reduce the amount of heat that we find in cities, what they can do through their personal lives to cool down their environments.
Well, Brian, Dr. Stone, this has been awesome. Uh, really appreciate your time and your expertise and insight and your passion for this topic. As we were saying, I think it's only growing. The
Yeah.
importance and the need is also unfortunately growing. And so, yeah, it's great to have people like you and the folks at your lab doing this incredible and important work for us. So
Yeah, David, thank you so
thanks so
much.
much.
Really enjoyed the conversation. Hope this is useful. Again, I think there's so many connections here for a science class. So I think this is a really productive way to illuminate, how science is so fundamental to our everyday lives. So really can see the utility of what you're doing and was glad to help. So if your students have questions, you can always reach out to me. Always happy to weigh in if I can.
Oh, great. Awesome. Well, thanks so much.
Okay, take care.
All right.
Okay, bye
Bye-bye.
bye.